In this lesson, we're going to be looking at tessellations. The outcomes we're going to cover are: describe and illustrate angle properties of regular polygons, explain using examples why a given property does or does not apply to certain polygons, identify and explain an application of the properties of polygons in construction, industrial, commercial, domestic, and artistic contexts, and solve a contextual problem that involves the application of the properties of polygons. So we're looking at tessellations. So what exactly is the tessellation? If you want something to tessellate, it means it has to cover an area using the repetition of geometric shapes, and there has to be no overlaps and no gaps. So here we can see a couple of examples of tessellations. The first on the left is an example of a tessellation using hexagons, and on the right we have a tessellation, a tiling pattern that is made up of squares. Now you may be familiar with tessellations without knowing what the term was. Basically, anytime something can tile, like the bricks in your classroom or in your school, or the floor is often a tessellation. Really, anything like that where you see different pieces joined together where there are no gaps and there's no overlapping. If there was overlapping in your floor, you'd be tripping up in your floor. If there were gaps in your floor, you could get your foot caught in a hole in the floor and trip up. So it's ideal that we have a tessellation where there are no gaps. The pieces fit together. They're flush with each other. They're sitting one on top of the other, but they're not overlapping, and they're not causing or not having any holes as well. So this is a pretty key piece of information right here. An object will tessellate when the interior angles where the vertices meet up add up to exactly 360 degrees. So for something to tessellate, the sum of their angles where they meet has to be 360 degrees. Otherwise, it will not tessellate. So we're going to look at an example now. Tessellating with a polygon. Jeff is a tile setter. His clients want to use tiles in the shape of a regular hexagon or a regular pentagon for the bathroom floor. Which shape will tessellate the area? So in other words, which would be the better tile shape to tile a floor with? For the hexagon, we can tile a few hexagons together like puzzle pieces to see if they work. So here we have a few hexagons put together, and they are clearly able to fit together very closely. There's not any overlapping, and there are no holes in the shape. So if we draw them out, or if we have pieces that we can put together, we can see whether or not something tessellates. Of course, there's always a mathematical way of doing this as well. Okay, so the tiles fit together here. There are no gaps and no overlapping, so they tessellate. To do it mathematically, we can also check by measuring the interior angles at all of the vertices where the polygons meet. Here I've taken the liberty of measuring the interior angles of all the polygons where they meet, and they all meet right here. So each of the three angles that make up this meeting of the vertices is equal to 120 degrees. We have 120 degrees in the top hexagon, we have 120 degrees in the left hexagon, and we have 120 degrees in the bottom hexagon. The interior angles where polygons meet up all have to add up to 360 degrees. And they do. 120 plus 120 plus 120 is exactly 360 degrees. So the polygons will tessellate. How about for the pentagon? because that was another option for tiling of the floor. If we try to fit the tiles together for a pentagon, like puzzle pieces, this is what we're going to get. Something of this nature. So when three pentagons are placed together, there is a gap that is clearly smaller than another pentagon. As a result, they will not tessellate. There's no way you can squeeze a pentagon, a regular pentagon, in the hole that is created in this shape. And the hole is, I'm looking at it specifically, I should point this out, is right here. I'm referring to it as a hole in our shape. Okay, so mathematically, if we measure the angles, what we're going to find is this. It's a regular pentagon. If you watched the last video, we talked about regular pentagons. And the sum of each of the individual angles in, or the measure of each, the measure of an angle in a pentagon, there we go, is equal to 108 degrees if it's a regular pentagon. So if we add up all three of the angles where these pentagons meet up, we're going to get 108 plus 108 plus 108, which works out to 324 degrees. So those three pentagons put together, the angles where they meet will be equal to 324 degrees. If we add another angle, another pentagon, to that, we're going to get 324 for the three that are currently there, plus another pentagon would be 108 degrees. So what we're going to find is that the sum of our angles is 432 degrees now for 4 regular pentagons. The maximum, or the number that we're looking for here, is 360 degrees. That is for any tessellating object. So seeing as how if we only have 3 pentagons, there will be 324 degrees, and if we have 4 pentagons, the sum of the angles is 432 degrees. It never will actually reach 360 degrees. So there is no way to add up those interior angles to 360 degrees. That means the tiles do not tessellate. So to summarize this section, a tessellation is a pattern that contains no gaps and no overlapping of shapes. We can determine whether or not a polygon tessellates if we physically tile them together. If you look at the side of your school or the side of a building that's made of brick, there is a tiling pattern there. It is a tessellation. We can also determine whether or not a polygon tessellates when we measure the sum of the interior angles where vertices of tiles meet. And when we do that, if the sum of the interior angles is 360 degrees where the vertices meet, the polygon will tessellate.